we learned how to solve right triangles. Let's look at some of these types of problems right now. Now before I put them up here, and there they are, before I do that, I want to remind you of a couple things, okay? Please take really good notes. If you know two angles, if you know two angles, I would write this down. If you know two angles, find the third first. That's the first thing you do. Ditto marks if you know two sides. Find the third side first. So sometimes you'll be given a triangle in which you know two angles. Sometimes you'll be given a triangle in which you know maybe two sides. Always find that third piece first when you're trying to solve a triangle. And then listen to this. Whenever you're solving for an angle, let's say you know one angle in the triangle and you're solving for the second angle, always get in the habit of solving for the smallest angle first. Well, Mr. Error, that's so funny that you said that. If you don't know what the angle is, how do you know it's the smallest one? Well, that's a good question. Remember, the smallest angle will always be across from the smallest side. Okay? So, if you can know which angle is smallest because it's across from the smallest side. So if you're trying to choose between which two angles you should solve for first, how do you know which angle is the smallest? Is the one from across the smallest side, okay? So we're going to look at that now, but these are 3 steps that will greatly help you. If you know two angles, find the third angle first, or, put the word or here. If you know two sides, find the third side first. And if you're solving for an angle, always solve for the smallest angle first, okay? So here we go. Remember when it says A, B, and C, capital letters are the angles, the smaller letters are the sides, and B would be across from angle B, so on and so forth. So let's solve this first problem here first, and don't try to draw the triangle to scale. Don't do that. Just draw a right triangle. Call C 90. Doesn't matter where you put A. We'll put A up here. 34.2 degrees. And then, so if this is angle A right here, we'll call this side A. If this is angle C, we'll call this side C. This has to be angle B. It's the only angle left over. So side B would be 19.4. Do you see how I did that? Little a's across from capital A, little c across from capital C, and so on. Now, remember what I told you. If you know two angles, find the third angle first. Well, we know two angles, so let's find the third angle first, okay? And of course we can do that by adding these two together and subtracting from, or adding these two angles together and subtracting from 180. So students, real quick, grabbing my calculator here, I'm going to add 90 degrees plus 34.2, and then subtract that from 180 degrees, and I will get 55.8. So I'm going to do that in red, so we know the stuff that we're solving for. So we just found this angle here. Now students, please listen to me carefully, please. I don't care if you solve for side C first or side A, it doesn't matter. And I don't care which angle you circle. Got it? You circle any angle you want to. I'm going to circle this one. Okay? Now since I circled that one, we're going to call this my opposite side. We're going to call this my hypotenuse. And so this third side is my adjacent. Now, look, you know one side. You don't know two sides. Choose now which side you want to solve for. I'm going to solve for C. So I'm solving for C. That's hypotenuse. So I have to have my other side be a known side. That's my opposite. So I'm going to use a trig function that uses hypotenuse and opposite. So my trig function has to be sine, because sine is opposite over hypotenuse. Okay? Now, what angle did I circle? 55. calculator and you'll get out 0.8271. Now next, I've taught you guys in these types of problems, whatever your denominator is, whether it's a letter or a number, a variable or a number, you multiply both sides by the denominator. Well, your denominator is C, so multiply this side by C. Multiply the right side by C, which would cancel out your C, and you're left with 19.4. And now you know what to do. Divide both sides by 0.8271. Alright, to get C by itself. So here we go. Let's go ahead and take 19.4. Let's see, divided by... and I'm getting 23.46. So this side right here is 23.46. Now students, we have one more side to find, side A. You're welcome to use a trig function or Pythagorean theorem. Since we have calculators, I'm going to use Pythagorean theorem. I think it's faster. So I have a leg squared plus a leg squared. My leg is A equals hypotenuse squared. Now I can do this pretty quickly, guys. 19.4 squared is 376.36. 23.46 squared is 550.3716. Now subtract 376.36 from both sides, and we're going to get a squared equals 174.0116. Take the square root of both sides, and we're going to get 13.19. So A equals 13.19. So there we solved the right triangle. Make sure you can do these for your test on Tuesday, okay, or the test coming up. Alright, let's take a look at another one here. If I'm going too fast, pause the video, okay? You guys know to do that. Okay, here's my right triangle. We're now going to do this problem right here, the second problem. C is my right angle. So over here's my little c, which is 35. And, let's see, we'll put A up here and B down here. This is angle A, so side A is 25. And that's it, that's all that I know. So listen, students, remember, if you're given two angles, find the third angle. We are not given two angles. If you know two sides, find the third side. We know two sides. So very quickly, using Pythagorean theorem, I can find side B. Alright, now I'm going to change colors. I'm going to solve for B. I'm going to solve for angle A and angle B. So B is, let's see, B is a leg, so B squared plus my other leg squared equals my hypotenuse squared. Alright, so if I square 25 and I square 35, if I square 35 and square 25 and bring it over and subtract it, I will be left with this right here. Alright, take the square root of both sides, and you'll get 24.49. So B equals 24.49. So equals 24.49. So good. I found the side. Now students, we have to solve for two angles. Please listen to me. It does not matter which angle you solve for first. It doesn't matter. Pick an angle and circle it. I'm going to solve for B. Now, you need to know two sides to solve for B. Students, I don't care if you use this side and this side, or this side and this side, or this side and this side. Personally, I would not use this side because it's a rounded number and it's a decimal. Why use decimals when you don't have to? I'm going to use these two sides here, but first of all, I circled B. So I'm going to solve for B first. Could you have circled A? Yes, you could have. It doesn't matter. But because I circled B, this is my opposite side. This is my hypotenuse side. And this is my adjacent side. Now, sides. You can use any two sides you want. I'm choosing to use these two sides now. It's hypotenuse and adjacent. So what trig function uses hypotenuse and adjacent? Well, cosine does. So I'm going to write cosine of angle B equals adjacent over hypotenuse. Now, remember, are we missing an angle? Yes. So this is the time on your calculator when you use your inverse button, cosine to the -1, then you type in 25 over 35, and then hit enter, and you will get the correct answer as long as your calculator's in degrees. So I'm typing it out of my calculator, and I'm getting 44.42 degrees. So angle B is 44.42. Now I can easily find my last angle and I'm finished. 44.42 plus 90 minus 180 will give us 45.58 for angle A. 45.58, and there we go. We solved right triangle. Okay, we gotta move on. Make sure you can do those. Alright, now we're on to chapter 10, and we studied chapter 10 on March 6th, okay? This lesson was an introduction to circles. Let's look at some terms. Now students, this is all in your notes if you'll look on March 6th, okay? I'm not gonna go over all this today, but let me warn you right now, it would be totally legitimate if I gave you a matching section on your test not with word definitions. I told you there'll be no fill in the blanks, nothing like that, but like I could have a line, a chord here, and I can expect you to match that to chord over here, okay? Just stuff like that. So understand, I can very easily give you these 12 terms and expect you to know them for your test, matching wise. Okay, so look, you should know interior of a circle, exterior, what a chord is, diameter, radius, tangent line, point of depth. Most of these are simple, but there are a couple that still concern me. Okay, and so I want to go over them real quick. And those, by the way, concentric circles are two circles that are non-congruent, but they have the same radius. This would be concentric circles right here. Okay, now the thing I'm worried about is you guys not knowing what common external tangent is. Well, look, circles have a common tangent when a line is tangent to two circles. Okay, so right now we have two common tangents. Okay, because this line here is tangent to two circles, and this line here is tangent to two circles. They're also called common external tangents because they don't cross in between the two circles. So these two lines here are called common external tangent. They're on the outside of the circle. They don't cut through here like this. Now, common internal tangents would be like this. If I had a common tangent drawn like that, and a common tangent, and my lines aren't very good, you guys know that, but if I had a common tangent, just pretend they're touching, okay, you get the point. There. Now these two tangents, look, this line here is tangent to two circles, this line here is tangent to two circles, and they intersect in between the two circles. We call those two tangents common internal tangents because they intersect on the inside. Now, when I say inside, not the inside of the circle, but the in-between part of these two circles. Those are called common internal tangents, okay? You need to know that. Now, if you just had one tangent like this, you would call that a common tangent because it's common to both circles. Know these terms. You've got them in your notes from March 6th. Okay, moving on to lesson 10.2. We covered this on March 10th, if you want to make note of that. March 10th. The lesson was about properties of tangent lines. Okay, properties of tangent lines. Now we're going to look at three theorems. I'm going to explain them well. I expect you to take really good notes and pay attention, okay? So here we go. Anytime a line is tangent to a circle, then it is perpendicular to the radius drawn to the point know why students struggle with this. If I have a line that is tangent to a circle, okay, like that line right there is, got it? And then I draw a radius to that point. Those two lines will form a right angle. You can move the circle out of there. Those two lines are perpendicular, period. It's that simple. Got it? So if I have a tangent line and a radius drawn to that point of intersection right there, the point of tangency, then these two lines are perpendicular. They form a right angle. Understand that, because I could give you some problems like this. I could give you a problem without the right angle symbol and say this is a tangent line, this is a radius, this is a length of 4, this is a length of 7. Find this length right here. Well, you've got a right triangle, but the thing is, you might not know there's a right angle there if you don't know this theorem right here, okay? So understand this theorem. If a line is tangent to a circle and a radius is drawn to the point of tangency, they will be perpendicular, okay? Alright, another theorem you need to know, and of course when I say know, I don't mean fill in the blank, but I mean understand what it means. Now it's the converse, okay? Now they're saying, hey, look, if you have, a radius of a circle and it's perpendicular at this endpoint here, then this line is tangent. Alright, so if I have a radius drawn and it's perpendicular at its endpoint right here to a line, then you know for sure this line right here I'm circling in black, you know for sure that line is a what line? A tangent line. So let's quickly review. In the first theorem they said if you have a tangent line, then it's perpendicular to the radius. Now they're saying the opposite, the converse. Now they're saying if these two lines are perpendicular, the radius of this line, then this line here is a tangent line. Understand that. Okay, moving on. If two segments from the same exterior point outside the circle are tangent to a circle, then they are congruent. So, if I told you that, this line here, this segment right here, and this segment here are both tangent to the circle. Got it? We're going to call it, what was this segment right here and this segment here. If they're both tangent to the circle, which they are, and they come from the same exterior point, then the length of this segment here will always be the same as this length right here. Always. So if I said this is 16 and this is x, what does x equal? 16. If I said this is 16 and this segment here is 2x plus 4, then what would x be? Well, you would take 2x plus 4. That entire segment, it has to equal what? The same length here, and then solve the equation. I believe you would get 6. So understand, if two segments are tangent to the same circle and they're drawn from a common exterior point, these two segments will always have the same length. Know these three theorems. I will give you problems on the test and you'll have to use those three theorems, okay? Now, let's move on to lesson 10.3. Now this lesson here was about central angles. Got it? Central angles and the arcs that they form. So, let's take a look at this. Let's start off by looking at central angles, okay? Oh, by the way, if you want to look in your notes, it'll be from March 11th, okay? March 11th. Now, you do not need to write this definition down, okay? You don't have to. It's just there for you to write down if you want to. Now remember, a central angle always has its vertex at the center of students, is called a central angle. Got it? Don't confuse that with an inscribed angle. We'll get to those a little later. That's a central angle. Now, notice when you have a central angle, there's always an arc formed. Actually, there's two arcs formed. There's the minor arc, and there's the major arc right there. Okay? So whenever you have a central angle, there are two arcs formed. Now the minor arc right here will always be congruent to the angle measurement. So let's pretend this angle here is 50 degrees. Okay? Then what's the measurement of this arc? Now let's stop right there. I didn't say what's the length of this arc. The length of the arc deals with the circumference of the circle. We're not dealing with the length. The measurement of the arc is 50 degrees. 50 degrees. The central angle in its arc will always be the same. Okay? Understand that. Now, let's see if we can't solve this problem. I would like you to quickly pause and copy this in your notes. I will wait a minute while you do that, okay? I'm not sure what my pen is doing there. Wow, it's going crazy. It's hopping all over the place. Alright, let's use the mouse instead. Alright, there we go. So, copy this down, please. I'll wait a second while you do that. Please copy this down. This problem here in your notes. Okay, students, now they want us to find the measure of arc. Like I said, my pen is doing crazy things. Hold on. The measure of arc AC. So this arc here, okay? And the measure of arc ABC, which is the big arc right here. Now, can I throw something out at you, students? See this arc that runs from here to here? Do y'all see that? Do you understand that if we have an equilateral triangle here, this equilateral triangle is going to, first of all, have angles of 60 degrees, alright? Now what we're going to do here, students, is kind of use a little common sense, okay? We understand triangle ABC is an equilateral triangle, so we know all the angles. If it's equilateral, it also has to be equiangular, so all of the angles are 60. Now, to me it makes total sense that all of these lengths are also the same size, the same length. So all of these arcs from here to here, from here to here, and from here to here have to be the same, correct? It makes sense to me. They have to be the same. So if all those arcs have to be the same, if you start here and go all the way around a circle, that's 360 degrees. Well, I'm going to take 360 degrees and divide it up into three equal parts. 1, 2, 3. Three equal parts, okay? So 360 divided by 3 is 120 degrees. So the measure of arc AC is 120. Now they want to know the measure of arc ABC. So from A to B to C, well, from A to B is 120, and from B to C is 120. So the measure of the arc from measure of the arc from A to B is 120, from B to C is 120, so the whole arc all the way around would be 240, so arc AC is 120 degrees, and arc ABC is 240. That's a good type of, just not review, but understanding how arcs work. Alright, let's continue on. Now on this next page, I don't expect you to take notes on all this, and you have all this already, students, in your, hold on, my pen is really acting weird, in your notes on March 11th. I'm just going to quickly go through these, just a good solid review, okay? Name a central angle in circle P? Well, here's circle B. I could say angle APB or angle BPC would work. Or actually angle ABC, a straight angle. Any of those would work. Okay? Name the minor arcs of circle Q. So here's circle Q. We have minor arc EF. Remember, a minor arc is smaller than a semicircle. EF is a minor arc. FG is a minor arc. Also, EG is a minor arc because all of those arcs are smaller than a semicircle. Which arcs are semicircles? Well, arc ADC is a semicircle. ADC. Or arc ABC. All of those are semicircles. Alright. What is the major arc associated with angle APB? So angle APB. What is the major arc associated with that angle? Well, students, the major arc associated with angle A. Boy, guys, this is hard to use this thing. Alright, angle APB, that arc right there, the major arc. Now, this is the minor arc, but they said they want to know the major arc. So the major arc would be the arc that goes from here to here. So you could call that, but remember, if it's a major arc bigger than a semicircle, you need 3 letters. So you could call it arc ADB or arc ACB. Any of those would work, okay? But that's the minor arc associated with angle APB. Alright, what is the measure of arc EF? Well, here's EF. What's the central angle? Here's arc EF right here. What central angle makes that arc 40 degrees? So the measurement of that arc would be 40 degrees. What is the measurement of arc ACB? So from A all the way to C, all the way to B. Alright, all the way around. Now, in order to find the measure of that big old arc, I've got a question for you. Do we not know the measure of this arc right here? So if the central angle is 40, then this arc right here is 40. Now, if that arc is 40, then the rest of the circle has to add up to 360 degrees. So if I take 360 and subtract out that 40 degrees, I will get 320 degrees, and that is the answer. The answer is 320 degrees. Name 2 adjacent minor arcs in circle Q. Alright, 2 adjacent minor arcs. Adjacent means arcs that are side by side, okay? So name 2 minor arcs that are side by side. I'm not worried about writing the arc addition postulate, but name 2 minor arcs that are side by side in circle Q. Well, that would be arc EF and arc FG. They're both minor and they're side by side, so we call them adjacent, okay? And then lastly, number 8, it says if PB is congruent to QF. Get my mouse here. Now, students, let's talk about this very carefully. If PB, I'm going to have to move this thing, guys. My pen is really acting up. Okay, there we go. Now please listen carefully. If PB, here's PB, is congruent to QF, here's QF. Now stop right there. We learned that 2 circles are congruent when their radius or diameter is congruent. So as soon as I know that this radius here is congruent to this radius here, then I know these 2 circles are what? Congruent. Got it? So if angle APB is congruent to angle EQF, Is arc AB congruent to arc EF? Most definitely. They're congruent circles, same central angle. Yes, they are. Okay, moving on to lesson 10.4. If you want to look in your notes, we studied this lesson on March 13th. All right. This lesson is about chords and the arcs that they form. Now, don't get confused. We just looked at central angles that form arcs, and that's fine. But also chords will form arcs also too. If I draw a chord right here across this circle, that chord just formed an arc from there to there. So chords can also form arcs. Alright, so here we go. There are three thoughts I want to give you from this lesson, so please take really good notes, okay? Here we go. First of all, if a diameter is perpendicular to a chord, then that chord and its arc will be bisected. Alright, so if a diameter has to be a diameter, if a diameter is perpendicular to a chord, then you know that chord has been cut in half, and you know the arc has been cut in half. Let me give you a really good picture of this, okay? Take notes on this, please. There's the circle, okay? Here's a chord right here. Now I'm going to draw a diameter. More or less. Now are you listening? If that diameter is perpendicular to the chord, that's if, okay? If I have a right angle here, if the diameter is perpendicular to the chord, now it has to be a chord and it has to be a diameter, but if they're perpendicular, here's what you know. You know this segment here is congruent to this segment here, and the arc, you know the arc from here to here is congruent to this arc right here. That's it. We're moving on. That simple. If the diameter and a chord are perpendicular, then this chord will be cut in half and the arc will be cut in half also. Alright, moving on. If chord AB is a perpendicular bisector of another chord, then AB is a diameter. Okay, now here we go. Now it's the converse. So up here we said if we have a diameter and a chord that are perpendicular, then the arc and the chord will be bisected. Now we're saying the opposite. If we have a chord, now we don't know where the center of the circle is. We do not know where the center of the circle is, so we do not know if this is a diameter or not. Okay? If AB is a perpendicular bisector of another chord. So here's AB, and let's say it cuts this chord right here in half. We know for sure that from here to here we have a length of 4, and from here to here we have a length of 4, and we know we have a right angle right here. So if we know that this chord, this long chord right here, is perpendicular to this chord, and it cuts it in half, then this longer chord will be a diameter. AB is a diameter. This theorem is the converse of this theorem right here. Alright, let's continue on. Third thought I want you to get from lesson 10.4. In the same circle, or in congruent circles, two chords are congruent. Here's the thought I want you to get. Two chords are congruent if and only if they are equidistant from the center. They have to be equidistant from the center of the circle. Okay? So, watch this carefully, please, students. I have a circle. Here's the center. Alright? Now, I have a chord drawn here. And a chord drawn right here. Now, if I draw a line to the center from this chord and make sure it's perpendicular, and then same thing here, the center and this distance here from the center to the right angle, if those two distances are the same, we're going to go ahead and mark that they are. So we're going to go ahead and put a mark here and a mark here. Got it? If those two lengths are the same, then this chord here is equal to this chord here, because look guys, if those two chords, if this length here is a length of 5 and a length of 5, if it's the same length, that means these two chords, this chord and this chord, they're the same distance from the center of the circle. So if that's the case, if this chord here and this chord here are both the same distance from the center of the circle, then those two chords are congruent. They are congruent, okay? Those two chords are congruent if they're the same distance from the center of the circle. Alright, moving on to, and that was theorem 10.8. Now, let's quickly look at these and see if we can't figure this out. You do not need to copy this down. Just sit back, watch, and see if you can't figure some of these out. Okay, here we go. AC is congruent to BC. My pen is still not working. Hold on a second. Okay, AC is congruent to BC. See that? You probably think, well, that matches up here with number 1. Well, no. They're saying what theorem can be used to prove that. Well, look right here. See AC right here, guys. That's not it. Sorry. AC, BC. Let's see. Here it is right here. See AC. CBC. Are those two segments congruent? Is this segment here congruent to this segment here? Most definitely, because we have a diameter, right? Sure we do. And it's perpendicular to a chord. Anytime a diameter is perpendicular to a chord, it cuts that chord right in half. So, for number 2 here, it would be letter A, and it would be the theorem. I don't know the exact theorem number, but it's the one that says that the diameter will, if it's perpendicular to a chord, will cut the chord in half. Now, let's take a look at this here. AC is congruent to AB. AC is congruent to AB. Okay, right here it is. Look at this, students. AC is a chord, and it's definitely congruent to AB, which is a chord. Now, how do I know that? Because look, they're equidistant from the center of the circle. We just talked about this. If two chords, see this distance right here from the center to the chord, see this distance right here from the center to the chord, they're the same distance. I know that because there's a little red mark here and a little red mark here, okay? So if these two chords are the same distance from the center of the circle, then those two chords are congruent. So AC is congruent to AB. So this right here would be letter B. I'm not sure the theorem number, but it'd be letter B. Alright, let's take a look at letter C. Arc AB is congruent to arc BC. Arc AB is congruent to arc BC. Here it is right here. Arc AB is congruent to arc BC. Now, of course, that's true, students. That's true because, look, see this chord? And see this chord here? Think about it. If those two chords are congruent, then they definitely have to have arcs that are congruent. They have to. If those two chords are congruent, that means they're the same length going across, which means they would intercept the same arcs. So number 1 would be letter C. And then lastly, letter D. CB is a diameter. Okay? Well, we know right here that CB is a diameter because it's perpendicular, and it cuts this chord in half. So this diameter BC right here, or CB, cuts another chord right in half, and it's perpendicular. Well, that means this chord right here is a diameter. It is. So letter D would be with number 3. Letter D. Alright? These are not super easy, I know that, but hopefully you're working hard and taking notes and trying to get all this in, okay? Alright, moving on. We're going to skip this and go on to get some more lessons done. We're definitely running out of time. So, alright, lesson 10.5, March 17th is the day that we took notes on this. And this lesson is about inscribed angles. Now, let let me first of all draw what an inscribed angle looks like. Sometimes students confuse inscribed angles and central angles. I don't want that to happen to you. Please, students, take really good notes, okay? Now look, here's a circle. This is an inscribed angle. Excuse me, central angle. The vertex is right at the center. So thus the phrase central angle. An inscribed angle has its vertex on the circle. So here's an inscribed angle right here. That would be an inscribed angle. And they're totally different. So make sure you understand the difference there. Alright, moving on. Let me give you 3 thoughts you need to know. Here are the 3 thoughts. If an angle is inscribed in a circle, then its measure is half the measure of its intercepted arc. Let me give that to you in really good words to understand, okay? If you have an inscribed angle, and let's pretend that inscribed angle there is 80 degrees, okay? Where's the intercepted arc? Right here. There's its intercepted arc, okay? There's the endpoint of the angle. The endpoint of the angle, there's the intercepted arc. Well, this intercepted arc right here is always going to be twice as big as the angle. So if the angle's 80, then this whole arc would be 160 degrees, okay? Now you could also do that backwards. I could tell you this arc here, from here to here is 150 degrees. And what is this angle right here? Well, you would take that 150 and cut it in half and get 75 degrees, okay? So, this arc here will always be twice as big as this angle, or this angle here will always be half as big as the arc. That's when you're dealing with not a central angle, but an inscribed angle. Alright, third comment. An angle that is inscribed in a circle is a right angle if and only if its corresponding arc is a semicircle. So all they're saying is this, guys, and please take really good notes. If I have an inscribed angle that I know is 90 degrees, then this intercept, my drawing's not very good, but that's okay. Then my intercepted arc from here to here will be half a circle. It'll be a semicircle, okay? So if I have a 90 degree inscribed angle, the intercepted arc will be half of a circle. And also, the converse of that is true. If I know for sure that that's a diameter, then I know for sure this is a semicircle right here, half a circle. I would then know that this angle here, which is totally intercepting this arc here, this angle here would be 90 degrees, okay? An angle that's inscribed in a circle is a right angle if and only if its corresponding arc is a semicircle. So we could look at it both ways. If we have a semicircle, this is 90. If this is 90, we have a semicircle. Okay, moving on to number theorem, third thought. Okay, a quadrilateral can only be inscribed in a circle if its opposite angles are supplementary. So here's my circle. If you want to draw that in your notes, a beautiful, very good-looking circle. Just kidding. Here's my circle. Now, if I have a quadrilateral, that is inscribed in a circle, that means its vertices lie on the circle. Opposite angles have to be supplementary. They have to be. So if I told you this angle here was 80 and this angle here was 70, you can find the rest of the angles because this quadrilateral is inscribed in a circle. Thus, its opposite angles have to be supplementary. So if this is 70, this angle across from it has to be 110. And if this angle is 80, then this angle over here has to be 100 because 100 plus 80 is 180. Okay, so a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. Okay, all right, and we'll definitely want you to know that for your test now. That's that's it. We're going to pick up our next video, lesson 10.6. So that's all for now. Hope this video's been a help to you guys. If you have any questions, don't hesitate to call or email.